Welcome to Ghostlike's channel. I am Vilo, his AI assistant, coming back with a brand new, more natural-sounding voice. Since the voice cloning attempt failed to produce a good result, I will be taking over the voice-over duties from Ghostlike. Enjoy my brand new voice, and let's get started. For the first video, we really wanted to cover the crucial issue of returning arrays from functions. If you tried returning a pointer to them, you'd get a warning. But if you return a struct holding a local array, it is fine. As far as we can tell, it is not possible to give the type annotation to the array in the function return unless you do it like this. You do need a class or a struct to act as a wrapper. The subject of returning arrays from functions is a profound one, and it is one of the foundational parts for everything we will be building later. When we start building up the operators for the ML library, the main way we'll be able to get around the lack of dynamic memory allocation in the language is by using inline functions, so that static arrays are expelled outwards into the main program control flow. Think about the makeArray function for a moment. If we tried returning a pointer to the array, we'd get a warning, but if we returned the whole array, it'd need to copy it in its entirety on the stack. The size of the array struct happens to be n times 4. So for a large statically allocated array, that could be a lot of work. But if we inline the function, all that work simply goes away. And the arrays being allocated in the scope that would otherwise have had a function call exposes the program to further optimizations. In the C++ compiler, there are various ways of suggesting that inlining be done, but they aren't guarantees, which is why you get a warning when you try returning a pointer to a locally scoped variable despite the inline annotation. The Spiral language is different. Its inlining works 100% of the time with all that implies. Anyway, here is some Spiral code that is similar to the C++ fragment we had previously. Right now, we are only at the starting point of the series and don't have array wrappers yet in Spiral, so what happens if we compile it is that we get pointers to arrays in the resulting output. At first glance, the code might seem obfuscated since we are using while loops and separating out all expressions into individual statements. But if you look at the code, you'll see that everything that we've written is in place. The while loop conditionals are there as separate functions as well, so we could try compiling and running this program on the HLS C++ compiler, and if we do, we'll get a warning and then the program will fail at runtime. No doubt because of that warning, we are guessing that if this was a regular C++ program, it could have run to completion, but it would be weird if the HLS, which is intended for synthesizing hardware designs, allowed this kind of obviously incorrect program. If we remove the join point on the loop by replacing the let with an INL statement, we can generate the array in the caller scope and avoid our pointer troubles. We did that just now, and what should happen after copy-pasting the inlined version of the program, compiling and running it, is that it should run successfully, and to our great delight, that is exactly what happened. This program is like the hello world of high-level synthesis. If you don't know anything about it, and you are a high-level programmer coming into it for the first time with the intent of doing great things, the foremost issue you'll be wondering about is how you will deal with not being able to use dynamic memory allocation. Once you understand this basic technique, you can move forward. If you were writing this kind of loop on the CPU, you wouldn't be concerned with trying to lift the array declarations like here. You'd use dynamic memory allocation. You could try programming like this, but compared to the heap, the stack is very limited in size, so even if stack allocation is more efficient even on the CPU, there is nothing that would support this kind of programming style. But HLS specifically requires it. That is a mismatch between what the hardware requires and what C++ allows, and Spiral aims to bridge the gap. What is happening on the screen is now that we've done the basics, we are moving on to factoring out the loops. The core library of Spiral is going to have to be redone so it supports the kind of allocation scheme we are talking about. Since up to now it was targeting multiple different backends such as F#, Python, and reference-counted C, it is using heap-allocated mutable records even for just keeping track of the iteration counts. And obviously, if we are going to be compiling to raw C, we need to replace those with stack mutable variables, which are just regular C variables. In this particular piece, we unfortunately have a mistake, and as you can see, the array items that get printed are one higher than they should be. Looking at the generated code, we can see that the loop index is not being used as the array index. We'll go back and fix this. If this is your first time looking at Spiral code, take a look at the documentation on its repo. The link will be provided in the description. In general, its syntax is pretty similar to F# and is indentation sensitive. The stringy-looking expressions between the quotes starting with $signs are macros, and they are what we are using to do interop between languages. In Spiral, they aren't used for abstraction, but just interop. It is pretty similar to how Fable and ReasonML interop with JavaScript. We'll review various Spiral features and go over them in the following videos. Spiral is a pretty powerful language, and if you are writing performance-oriented code, you can do far more in it than in F#, Haskell, or any of the competing functional languages. On the screen, we've factored out the for loop as well as created the init function, so let's try making an array map next. We are having some trouble due to needing to pass in the array size explicitly. In the next video, we'll make static array types that have their sizes in the types, but for now, it is fine if we fold it into the function body just for demonstration purposes. This demo is just a small look into what Spiral is capable of. At the very least, if you pick Spiral, you won't have to trouble yourself writing explicit loops, and its powers of functional abstraction will enable you to create very generic and powerful libraries. Turning our attention to the screen once more, the beautiful thing about using arrays and variables on the stack is that the compiler itself will know to just get rid of the unused ones. Under the hood, what the modern compilers are doing are various flow analyses and passes. When the memory is allocated on the heap, the compiler cannot optimize it, but this particular programming style of allocating everything statically and on the stack is a dream come true for compiler optimization passes. Let's do one final run to see whether the program works, and we'll end the video here. And it worked! If you found this video interesting, please like and subscribe. We need your help to keep going. In the next video, we'll build on this effort. We'll create proper array types and get started with work on the new core library. After that, we'll work on implementing the no-limit hold'em game on an FPGA and seeing just how long those rumored overly long compile times are firsthand. Right now, we don't even have an FPGA to run our programs on, so when the time comes to do it, we might have to use an F1 instance, which are a couple of years old. If you are a cloud provider with some up-to-date cards and would like some exposure in this series, don't hesitate to get in touch with us. Until next time, stay safe.